Hello, and welcome to this episode of Madison's Chemistry. Today we're going to be distinguishing between Arrhenius, Bronsted Lowry, and Lewis acids and bases. So the way that I've set this up is first you can see that I've written Arrhenius, then Bronsted Lowry, and then Lewis. And the reason that it keeps getting bigger and bigger as we go along, as you'll see here, is because basically Arrhenius is the most specific. So if something is an Arrhenius acid or base, it's also Bronsted Lowry, and it's also Lewis. But if something's Lewis, it doesn't necessarily mean it's Bronsted Lowry. So I hope that this kind of makes sense, and as we go along, I think it'll begin to make more sense. Okay, so I've written on the sides what each of these mean. So if it's an Arrhenius acid, that means in water it's going to want to form H+. So a classic example on a Arrhenius acid could be HCl. So we add water, and we know it's going to go form H+. And similarly, an Arrhenius base is going to be something like a metal OH going to go form OH- plus Na. Right? So then, if we wanted to talk about what a Bronsted Lowry acid or base is, this is going to be something that donates an acid, or donates a hydrogen. So an example, let's say we have a generic acid, let's call it HA, and we put it in water, and it forms A- plus H3O+. Okay, so here we can see that it donates its hydrogen to water to make H3O+. So that makes it a hydrogen donor. Okay, so if we want to talk about conjugates here, we could also do that. So this is our acid and conjugate base, and this is our base and conjugate acid. And if you want to figure out what the conjugate acid is going to be, the conjugate acid is always gaining a charge. And if we know that there's going to have to be still a net charge of 0, right? Because we can't just get a charge from nowhere. So if this is gaining a charge, this means this has to lose charge. So the conjugate base should always lose a charge. Okay. And then similarly, if we're talking about a Bronsted Lowry bases, it's going to be a hydrogen acceptor. So we could say it's base plus H2O goes to BH plus OH-. So as we can see here, this is going to be accepting a base later, or a hydrogen later. So this is our base, the conjugate acid, and conjugate base. And some things that wouldn't be considered an Arrhenius acid or base, but would be considered Bronsted Lowry, would, for example, be ammonia. So that's something that doesn't necessarily 100% dissociate to form OH-, but it is going to be a Bronsted Lowry acid, or a Bronsted Lowry base. And similarly, NH4+ could be an example of a Bronsted Lowry acid because it will donate its hydrogen, but it's not an example of an Arrhenius acid. Okay, so let's keep going. So lastly, we'll have Lewis acid or base, and this is probably the most confusing because this is the one that we see the least of. But let's say we have something like Mg2 plus Cl minus goes to go form MgCl2. So we could draw an attack. So we have all our electrons here. So this can go and attack here. So this magnesium is actually accepting this pair of electrons, so that would make this a Lewis acid, and that would make this a Lewis base. So that kind of goes over what's happening with a Lewis base. So Lewis base are going to donate its pair of electrons, which we'll see, and Lewis acid is going to accept a pair of electrons. A lot of times Lewis acids are positively charged, and a lot of times Lewis bases are negatively charged.